Hey everybody, we are in our next lesson for Unit 10, Logarithmic Functions. Today we're going to be solving exponential application problems. So as always, we start with our topics for the day. We have the log song, we have exponential applications, and then you'll have some practice time for you guys to start on today's assignment. So here's your log song.
One rolls upstairs, over and stairs, rolls over your neighbor's dog. Comes straight for a snack and sits on your back. It's log, log, log. It's log, log. It's big, it's heavy, it's wood. It's log, log. It's better than that, it's good. Everyone wants a log. You're gonna love it, log. Come on and get your log. Everyone needs to know now.
Log from Blammo.
All right, let's get going with today's lesson. So in some previous things that we've done in our exponential unit, we used the compound interest formulas where we have our stuff compounded a certain number of times per year. And then we also have the PERT equation where it is continually compounded. That means every second of every minute of every hour of every day, of every week of every month of every year. Okay, so those were straightforward for us. We would just find our final amount when we put in the initial value, had a rate, and talked about the number of times compounded per the amount of time. This set, we're actually going to be working our problems backwards. So we're going to be looking for how long does it take for something to double or triple or become a certain amount. So here is our first example. How much time would it take for an initial investment of $500 to double if invested in an account with a continuous interest rate of 6.75? A couple of things we got to remember, or we've got to pull out from our info. So we have A equals P because it says continuous. This is going to be our PERT problem. E is continuously increasing. E to the power of RT. A is our final amount. P is our beginning or our principal. We are beginning with 500. Our final amount is if we double it. So 2 times 500, which would be $1,000. The rate that we have is 6.75, so 0.0675. And the time is what we are looking for. That's our big question mark. How many years does it take for that to happen? So we're going to set up our problem. A equals P multiplied by E to the power of RT. Our A value, our final amount is 1,000. That equals the initial investment 500 multiplied by E to the power of 0.0675 T. We are now going to work our problem backwards, isolating this base with our exponent so we can get the t all by itself and solve for time. We'll do that by dividing through by 500, and 1,000 divided by 500 is 2. That equals e to the power of 0.0675 t. In order to undo base e, remember that is log base e, or the natural log will undo this. So I can take the natural log of both sides of the equation and it will undo e to the power of all of that stuff. This leaves us with the natural log of 2 on the left-hand side of the equation now just equals our exponent, 0.0675 t. And what I would like for you guys to do is just put it all in the calculator at one time. So show your work for dividing by that interest rate that we have in decimal form. So our time equals the natural log of 2 divided by 0.0675. So natural log of 2 divided by that will give us a value of 10.2688. So real quickly, that means about 10.3 years is how long it takes for our money to double. So that's quite a long time for our money to double. All right, that's our first one. Let's try a few more. Here we go. How much time would it take for an initial investment of $1,000 to triple if invested in an account with a continuous interest rate of 5.5%? Very, very similar setup. Again, continuous interest rate. So we have A equals P multiplied by E to the power of RT. We have A as our final amount, P is our initial, the rate, and then our time. So our initial investment is 1,000. That's our P. We want it to triple. So 3 times 1,000 would give us 3,000. The rate is 5.5%, which we changed to be 0.055. And the time is our big question mark that we're actually looking for. Substitute in, solve like we just did on the last example, and solve for our time. How long does it take for the money to triple? So 3,000 equals 1,000 multiplied by e to the power of 0.055t. Just like we did in the last example, in order to undo a base of e, we first have to isolate it. So we are going to divide through by 1,000 on both sides. That will give us 3 equaling e to the power of 0.055t. Now we get to undo the base e. The natural log and e completely undo each other. Again, it's like adding, subtracting, multiplying, and dividing. So I'm going to take the natural log of both sides of the equation, which leaves us with the natural log of 3 equaling the exponent 0.055t. And just like we did in the last one, to be super precise, go ahead and put everything in the calculator at once so you can get your t value by itself. So the natural log of 3 divided by 0.055 gives us a value of 19.9748, actually. So this is almost 20 years for the money to triple. That is a ton of time. Okay, so that would be 19.97 years if you want to be kind of a little bit more precise. That's a heck of a long time, guys. Holy cow. All right, example 3. You invest $20,000 in a savings account that pays 1.3% interest and is compounded monthly. All right, so that's going to be a different equation. This is our compound interest where we have a number of times. So it's A equals P multiplied by 1 plus the R over N. That's the number of times compounded, raised to the power of NT. Number of times compounded times your time. All right, let's substitute in. You invest $20,000. So $20,000 into a savings account that pays a rate of 1.3. So that would be 0.013 is my rate. So 1 plus 0.013 over compounded monthly. There are 12 months in a year. So divide that by 12. And then answer our question, how much money do we have after 15 years? So this one's actually looking for our final amount, where our t equals 15. So our exponent has to be the number of times compounded times the number of years that we have. Type it into your calculator as is. So 20,000 multiplied by 1 plus, and then you got to use that fraction, 0.013 divided by 12. And then your exponent, you can type it just as it is, 12 times 15. And this gives us a final amount of $24,303.65. And that already has been rounded correctly to the hundreds place. All right, now we want to know how long is it going to take for the entire amount of money to the original to double. All right, so if I'm doubling, if my initial investment is $20,000, my doubling would be $40,000. So this equation is going to be 40,000. Now we know it's going to be longer than 15 years because 15 years only got us a little bit more than $4,000 on that initial investment. All right, so 40,000 equals 20,000 multiplied by 1 plus. I still have the same rate, the same number of times compounded, but my exponent becomes 12t because that's what I'm looking for. Divide both sides of the equation by 20,000, so that gives you 2. And if you like, you can go ahead and simplify in parentheses 1 plus the 0.013 over 12 gives us a value of, let's see, that is 1.00108. Okay, we're going to take it out to the third decimal. So we're going to change this to be 1.001. That's in parentheses to the power of 12t. Okay, now we're estimating a little bit. We're actually double rounding in our problem. We typically don't like to do that, but it's going to get us close enough. In this case, there's no way to make both of these have the same base. So we can just take the log of both sides of the equation. So I'll have log of 2 equals log of 1.001 to the power of 12t. That power can go to the front. So log of 2 equals 12t times log of 1.001. And now to isolate the 12t, I can divide both sides of the equation by log of 1.001. You can type this value, log of 2, divided by log of 1.001 into your calculator and see what value you get. Again, we're kind of rounding part of the way through. I don't really like to do this, but might be a little bit easier to keep up with it. So log of 2 divided by log of 1.001 is 693.49, and that is going to equal 12t. So when we divide both sides of the equation by 12, we get that our t value is 57.79. Oh my goodness, it takes 57.8 years for the money to double. Holy cow, that is ridiculous. Whoa. But that's the correct answer. Okay, now we're going to look at an actual decay function, talking about a half-life. You guys have heard about this stuff in some of your science classes. The half-life of cesium-137 is 30 years. So you'll notice that's actually up here in our exponent, the time divided by the time it takes for every half-life to occur. So we have our equation C equals C sub 0, which is our initial amount, equals 1/2, that's because it's decaying, it's a half-life, to the power of t divided by 30. And again, that 30 is the time per half-life. So how long it takes for one half-life to occur. If there are 15 grams at the beginning, after 25 years, what was the initial amount? Okay, so C equals C sub 0, 1/2 to the power of t over 30. If there are 15 grams, that's what I'm ending with. After 25 years, 1/2 to the power of 25 over 30, what's the initial amount? C sub 0. And hey, we're at the end of class, but we're not. I'm going to finish this. So we are going to simplify 1/2 to the power of 25 divided by 30. It's going to look really weird. So 15 equals the initial amount multiplied by 0.5612. And then you would divide through by that. So 15 divided by 0.5612 gives you the initial amount. 15 divided by 0.5612 gives us C sub 0 equals 26.73. So we have about 26.73 grams as the initial amount. It's what you began with. It would probably have been more like 27 grams, but we're just going to call it that. All right, I'm going to stop this one. We will come back with a few more in another video.